In this webcast, we're going to work together some of the examples that are in Worksheet 7E about the energy of satellites. So the first problem is talking about a satellite in orbit around the Earth, and they're telling us that it has an altitude of about 700 kilometers above the surface of the Earth. And so the first question is, what's the gravitational potential energy of this system? The system comprises the Earth and the satellite. They're reminding us that the zero reference point is when the separation is infinity. Okay? So I'm just going to get the formula for gravitational potential energy, and I need to be very careful to remember that the gravitational potential energy of a satellite is always negative. So there's a negative g, our universal gravitational constant, times the product of the two masses, and then divided by the orbital radius. I'm just going to go up here, or I'll go here and I'll calculate that orbital radius. It should be the radius of the Earth plus the altitude. To be careful, I'm just going to calculate it separately so that I don't use the wrong one. So there's the radius of the Earth in meters. And they gave me the altitude in kilometers, but I need to make sure that I put that in meters, okay, because I want to work in standard units. And so I get that the orbital radius here is 7,080,000 meters. Okay, now to go back to finding the gravitational potential energy, it's going to be negative g, the big mass, which is the mass of the Earth, that's the central body here, times the smaller mass, which is 9,800 kilograms, divided by that r, the orbital radius that we just found. Okay, and so when I find this, it is going to be negative. Sorry, I messed up the first time that I had a little flat finger on my calculator. So I get negative 5.512 times 10 to the 11th joules. So that's the gravitational potential energy of this satellite. Now what about the kinetic energy? The kinetic energy, the formula for that, it's positive. It's g times the product of the masses divided by 2 times the orbital radius. It's the same orbital radius, right, that we had in part A. If I compare these two formulas, I can see that the kinetic energy is half of the absolute value of the gravitational potential energy. So I'm not going to plug all those numbers in. I'm just going to take the number that I found, divide it by 2, and of course make sure it's positive, and I get 2.756 times 10 to the 11th joules. That's the kinetic energy of this satellite. And then as far as the total energy is the sum of the gravitational potential energy plus the kinetic energy. In terms of a formula, it's negative g times the product of the masses divided by 2 times the orbital radius. But I know how much that number is. That's what I found in part B. If I just put a negative sign on that, I have this. The total energy is 2.756 times 10 to the 11th joules. Only it's a negative amount. Okay. Let's go on to another one here. Let's look at number 2, where we have something with a circular orbit, and initially is at an altitude of 359 kilometers, but then we want to move it to a higher altitude of 35,800 kilometers. They're asking us to find the difference in energy. That's the work that had to be done to transfer energy into this satellite system to raise it to a higher orbit. Okay? And so, let's see here. Maybe I should just find my initial orbital radius is going to be the radius of the Earth plus the initial altitude. So that's going to be 6.38 6 plus 359,000. So that's 6,739,000 meters. But the final orbital radius is going to be the radius of the Earth plus the final altitude. Make sure that you add the altitude in kilometers. That's 35,800 times 10 to the third meters, right? And so we get 42,180,000 meters. So there's quite a big difference between the two orbital radiuses. The energy that we're looking for is the change in the total energy of the satellite system. And so that's going to be the final total energy minus the initial total energy. And if we remember the formula, it's negative g times the product of the masses divided by the 2 times the orbital radius. In the final case, it's the final orbital radius. And for the initial total energy, it's the initial orbital radius. So I'm going to just factor out the stuff that's in common here. I can factor this stuff out. The negative gm, I should have, I'm sorry, brought my g here to include both masses. I can factor all that out, and it makes the math just a little bit easier. So it's going to be negative g times the product of the masses over 2 times 1 over the final orbital radius minus 1 over the initial orbital radius. So it's going to take a little bit of math here, but I can do this. I've got what I need to plug in. I'm going to do this in two pieces. I'm going to do the front piece first because I want you to see that that's a negative number, right, because of my negative sign. So g times 5.97, 10 to the 24th, times 9,550, and then divided by 2. So I get negative 1.901 times 10 to the 18th. But that's going to be multiplied by the stuff that's in my square brackets. So that's going to be the inverse of the 42 million number minus the inverse of the 6 million number. And I get a negative 1.247 times 10 to the negative 7. So see, I'm going to have a negative quantity times a negative quantity. This is going to turn out to be a positive amount of energy that has to be transferred into the satellite system in order to raise it to this higher orbit. And I get 2.371 times 10 to the 11th joules.